Okay. So one of them is, so we are going to look at assumptions that goes in this radiation fields. And what we want to do is look at same results, but from a different perspective. So one of the things that we did when we talked about radiation, we started by radiation from a single charge and we calculated basically the Larmor value. And we saw that it's proportional to the acceleration squared, and we have used it many times. Okay. And then we went to the case where there were a number of charges. And at that time, we realized that a number of charges, if they are local, and if the distance at which I'm looking at the field is far away, then I can, in some sense, don't care about the local small distances. And there were some assumptions. And then we can sort of look at the total charges and think of a dipole over there. And the radiation was from a dipole. Okay. And that was the famous dipole formula. And we use the dipole formula in many things. Now, to do that, we calculated what was, so to know radiation, we have first, we of course, we went to, remember, first we started by looking at the Lorentz gauge. Then in that Lorentz gauge, we found that the equations, the solutions to the potential equations gave us the retarded potentials. Once you have the retarded potentials, we can find out what is the field at this far away point. And once we know the fields at the far away point, we can look at the Poynting vector, and that gives us, in some sense, the flow. Now, we have also realized that when we talk about radiations, things are not always so trivial, so simple, and we came up all these fallacies. And so the whole thing is that how we connect the charges that are doing this radiation, the radiation which is impinging on the charges, how complicated we want to be would mean how extensively we look at all these things. So first of all, you can think of the charge being at rest. You can try to oscillate the charge by putting a radiation, and then this radiation will again, oscillating charge will give radiation. So it all depends on how much or how extensively you want to basically take it every effect. Now, one of the things that we should realize is that if we divide this whole system of whatever is making the charge accelerate, so something has to make the charge accelerate. Okay. That is giving energy to the charge. But then the radiation field, that energy is actually coming from the charge. So we can think of radiation and calculating this radiation at the power by looking at energy equations. Okay. So that's what we first want to do. And then we'll see that we have looked at this dipole and looked at radiation in terms of dipole, whether we can slightly extend it. And when I say I extend it, I don't mean going to quadrupole, because general charge distribution will always have dipoles and quadrupoles, but quadrupole typically will be suppressed. And that we found out when we are looking at, remember, why does a circular where the current is flowing, why does that radiate? So we saw that every higher powers were suppressed. So let's start. Let's start with the first issue. So let me share my screen and try to look at this radiation from another point of view. So just give me a moment. So screen I want to share. Oh, that's right. Let's see. Share my screen and So this is what I was saying. So I will sort of show you things that I've written down today that will make things a little faster, and then in the second part I will start writing again. Okay. So as I said, today we are going to continue our discussion on radiation and look at some of its dynamics. Okay. And the idea, the first thing that I want to show is that, so as I told you, we already know that the energy or the momentum goes from the source to the field. Of course, that basically means the source has some source of energy itself. So we are not talking about that. That would be another aspect to it. Okay. So this energy that goes to the field, the radiation that comes from the source. Okay. And sometimes we realize that when the source gives radiation, then this radiation can back react on the source, and that was radiation damping. Remember? So that was, so I'll try to do it like this. So that was radiation damping. Okay. And we looked at radiation damping by looking at the work that was done and equating it with the Larmor radiation. So if you remember how we did radiation damping, we calculated the work that was done and equated with the Larmor radiation, and that gave us some idea of the radiation damping. Now we can take this idea a little more and now ignore radiation damping, because radiation damping is subdominant, and look at the work done again. Okay. So what we want to do is basically whatever things happen, however this source gives this energy to the field, what is interested is that we must basically be looking at conservation of energy. And we didn't do our calculations using conservation of energy in the beginning. So we are going to use that. Okay. So the conservation of energy basically means that we have to calculate what is the work done by the current or the charges locally. The important word over here are many. First of all, we're looking at conservation of energy. That's one important word. Then the energy comes from the rate of the work which is being done by the current. And a very important word is locally. So we are going to now look into our radiation and energy conservation from a local consideration. So look at what the charges are doing locally. Initially, remember we calculated, we established how a field due to a local charge would be, and then calculate the radiation by looking at the field. Now I'm going to look at how the work will be done locally, and then say that, okay, if this is the amount of work done, then some of it will go to the radiation, and we'll see whether that gives the same answer or not. Now to calculate the work, okay, the work is basically your force times velocity, and if the velocity is much less than, so in the non-relativistic limit, I can basically ignore the V by C cross B term, and so your work comes out to be this. Okay. And Q and V gives you your current, so I can write it in terms of the current. So if there's a local area where there's a current J, current density J, then this J dot E, an integral over the local area, gives you work done. So the next step, I understand that I'm going fast because I'm not writing, but idea is to go fast, that's why I'm doing this. So the next step, what I want to do is I want to replace my J in terms of the electric and magnetic fields. Okay. So I can use my Maxwell's equation. So this is a local Maxwell's equation. It's a local system. So I'm doing everything locally. So my curl of E will give you my del V del T and J. And I put my J back in this equation above. So get the local energy conservation. The important part is local. So everything over here, Maxwell's equations and local equations, remember? So whatever you're doing over here is local. That's a very important thing you want to keep in mind. You're doing everything local. So your J dot E, if you calculate, then you will find that I can write this. This is something you can, you can verify in a three line homework. So this is a 3-line calculation. That your J dot E, when you calculate your J dot E, that will basically give you this equation. which will give you a del T of E squared plus B squared by 8 pi and a divergence of C by 4 pi times E del T. This is what we will get. Now this has to go inside the integral of d cube r. So this must go in over here. Okay. And when you do that, what you get is this equation. So the integral over the local volume of minus j dot E is d dt of the integral of E squared plus B squared over the local volume and a surface integral of C by 4 pi E cross B. When you look at this formula, which comes from the work done, you see this formula. So work done is on the left hand side, the work done by the local current, that's on the left hand side. That gives rise to two terms. One is a total derivative term, which is, and it's very important to realize that it's a total derivative term, ddt, of something which is E plus B squared plus B squared 8 pi. So that is the energy. Okay. So E squared plus B squared is the energy, total EM energy in a volume. Okay. So the rate of change of the EM energy plus a term which is your P, so which is like a flux. So these three terms basically is on the left hand side, I have the rate at which the current is transferring energy to the field. So that's the work done. Okay, that's what is the left hand side. And the right hand side, this energy that's going to the field are doing two things. One, it is escaping out, and the escaping out is the rate of flow of energy, which is this P. So this part is escaping out. Okay, so that is the radiative power. That's the escaping energy, which is going out of the volume. So that's one thing. Whatever cannot escape is increasing the total magnetic energy of the volume. So the work done by the charges locally is doing two things. It is increasing the local EM energy, and the rest of it is escaping out and going to the faraway region. Okay, so these are near field, and the rest is going to the faraway region. So this tells me that if I try to calculate this, if I try to calculate the work done, then this gives me an alternative way of calculating what is the radiation flux, what is the Larmor flux that we did before. Okay, so what is the radiation flux from a charge in a local region? Okay, that's an alternative way. This is different, as I said. So I'm going to say it again. This is different. So this is another way. So it is done by calculating the work done. This is our way. And we discard this ddt of t. So we discard the total time derivative, and the rest basically becomes the flux. How is this different? Again, to say previously, this P was calculated for the far field configuration. So we looked at things. If you go back to your Larmor and the dipole radiation, remember we did the case where R was much greater than R naught or whatever, depending on how we have defined over there. And we have done this for this different cases, which is far field. In contrast, now we are not doing far field. We are basically looking at the field E inside the current distribution. So everything, the work done is done by looking at the E field at the location. We're not looking at the E field, which is far away. Whatever we left will be the energy that is lost, that will go far away. Okay, so that's what we want to do. So now how do we want to do it? So the way to do it is very simple. There's a little bit of complicated calculations. Some of it I will skip jump. You can do it, but I'll not skip jump everything. I'll tell you how to do it. So we're going to consider the dipole radiation. Okay. So we'll consider dipole radiation. And obviously we are going to consider cases where the things are non-relativistic, because we have, remember, we have neglected V by C cross B term in the very beginning itself. So everything is non-relativistic. Okay. So we want to calculate the work done locally. Local E is given by this relation. It depends on the two potentials, the vector and the scalar potential. Okay. So these are. Now, do we need? We want to calculate something which should give us the flux, which we dipole flux or whatever, the flux of radiation. And remember the Lama formula, the flux of radiation went as 1 by c cubed. Okay. So in the dipole radiation, remember the Lama formula, the quantity goes as 1 by c cubed. Okay. So we need to calculate this equation up to 1 by c cubed term. We want to calculate something where we must have 1 by c cubed term at least, or we don't need anything more than that. So phi has to calculate it to be 1 by c cubed. The phi doesn't have a c itself, but the a needs to be expanded to 1 by c squared. So then E is 1 by c cubed. Okay. So if I expand my E, where I expand phi to 1 by c cubed term, if I expand my A to 1 by c squared term, then due to this 1 by c, which is there with the del A del T, I get everything to 1 by c cubed. Okay. Now we are talking about radiation. So we need to talk about the charges locally. Okay. And we need to talk about something which is local, but we have to be careful of how we expand it. So remember in the Lorentz gauge, our phi and A were given by this formula, right? Where the potential due to whatever charges were there, but even slightly away from the charge, if the charges are moving, then the potential is given by this formula, where the rho and the j were at this retarded time, and this retarded time, if you look carefully, has a 1 by c term. Okay, so retarded time has a 1 by c term. So the idea would be to expand my phi and a in terms of this retarded time. So expand it in a series and keep terms up to 1 by c cubed in phi and 1 by c squared in A. Okay, so that's what we're going to do. So we have this Lorentz gauge phi and A, the retarded potentials, and we're going to expand it. So let us expand the phi. Okay. So when I expand the phi, I have to expand the zero term, the 1 by c, the 1 by c squared, and 1 by c cubed. Zero term is basically rho by r, the distance r minus r prime. That's the zero term. Okay. Then I have 1 by c, r minus r prime in the series. So first thing is the del rho del t, because I am expanding in t. Okay. I'm expanding in t. So it's, the t comes with this 1 by c. This t prime I'm expanding over here. Okay. So I've got del rho del t. The next term will be the next in the series. Okay. So that's half r minus r prime squared and del 2 rho del t2. And remember, all of them have a denominator is r minus r bar coming from here. So this is what this current kilometers are here. So then comes the fourth term, which is the cube term, and that will have 1/6 1 by c r minus r prime cube, and then del 3 rho del t. So we have del rho del t, we have del 2 rho del t2, and we have del 3 rho del t3. That gives up to 1 by c cubed term. And then we can neglect the terms which are more than that. That's what we're going to do. Now, if we look at these terms and look at the second term over here, the second term is basically dqr del rho del t, right? That's the second term. So 1 by c I can take out, r minus r prime I can take out. That's it. But it's basically this volume integral of del rho del t. That's the volume integral of del rho del t. If I integrate the rho, that's the q. So this is basically dq dt. Okay. So that's the rate of change of charge. But it's a conserved system. Your charge is conserved locally in that volume, no charge is going out or coming in. So dq dt is 0. So we can get rid of this second term. Don't need the second term. So we are left with 3 terms, one without the c, and one with c squared, and one with c cubed. Okay. So I can write down finally my phi rt in terms of the first term, which is basically rho by r. The second term, which is 1 by c squared r into del rho del t. And the third term, which is 1 by c cubed r squared into del 2 del 3 del t3. So keep this in mind. We are going to use this later. Okay. You will have all these notes, so you will be able to look at it, and there's no don't have to be don't have to remember it very well. But when it's not very difficult, I will just put it over here just for you to see that it's straightforward over here. The first term remains whatever. The second term is gone. The third term I have basically divided this r minus r prime in the denominator. So it cancels 1 power of r minus r prime in the numerator. So that's 1 power of r minus r prime remaining. And the third term is 2 powers of r minus r prime is remaining. That's it. Okay. And minus plus minus the way it goes. Similarly, we have to expand our vector potential also, which is the A. Now remember, the vector potential, we do not have to expand up to the third order because we already have 1 by c remaining. So in the vector potential case, we need to expand up to the second order. Okay. So this is what you have done. Expand to the second order. There's a 1 by c term is there. And then I have 1 by c squared term is there. So this is how I expand. And this is what we get. Okay. So we have a integral over the volume of current density by r minus r prime. And then there is an integral of the volume, but the derivative of the current density. Now, if you think of local charge conservation, then the derivative of the current density is related, or the current density rather, is related to the del rho del t. Okay. And so you see that the dipole moment over here, which is defined like this is related to the current density. And that's why the derivative of the current density comes as a double derivative of the dipole moment. So this term over here is nothing but the double derivative of the dipole moment. Okay. Because the current density itself is the first derivative of the dipole moment. And the dipole moment comes because I have an r times rho. And this comes from a local charge conservation. Very simply, it's not very difficult to show. So this second term, very interestingly, gives us that d double dot term. But remember, we still don't have the flux, which remember had a d double dot squared. So at present, we have just got a d double dot. So this is how I expand my A. So now we have to multiply. So we have to go into this case where is it? This E is over here, so I have to do J dot E. So I have to multiply all these phi's and A's with G. I have to dot it with J, right? So go over here, dot it with J. Now, before I go to next step, it turns out that we can actually simplify the phi term, one of the phi terms, even more, one more times. So remember, the phi will come as in the E, it will come as minus grad phi, because we want to do J dot E, and E is minus grad phi minus 1 by c del A del t. So the phi will have a grad operating on it. So a grad will be operating on all of these. Okay. And if I operate the grad on the third term of the phi, so if I operate the grad on this term, I can simplify this a bit. So how will I do it? I do it like this. So this was the third term. Remember, the one in the bracket is the third term. Minus 1 by 6c cubed, volume integral locally, r minus r prime squared, because it was r minus r prime cubed, but there was r minus r prime at the bottom, so got rid of one of the powers, and the third derivative of the rho. When I have a minus grad of this grad acts on the r minus r prime. Okay, so get rid of one of the power. So that gives only r minus r prime, and 2 comes on the front. The 2 cancels with the 1 by 6c, so it becomes 1 by 3c cubed. And we are left with, I can take out by ddt outside, we are left with the third derivative of this quantity, which is over here. That's how I get it. Because the grad acts on the r, so that gives you only 1r, one of the powers are gone. The 2 cancels with the 6 to be 1 by 3. I can write it like this. Now look at over here, this thing inside the integral is nothing but the dipole moment. It's r into rho. That's the dipole moment. So this grad of the c cubed term in the phi expansion is nothing but 1 by 3c cubed, the third derivative of the dipole moment. And so this is this. Okay. So the term over there, one of the term in the phi expansion leads us to a dipole moment, the third derivative of it. One of the term in the J expansion leads to the second derivative of the dipole moment. So we are getting the dipole moments already in our expansions. Now I have to combine these two. When I combine it, I have to do this. Okay. So I want to calculate this J dot E. So it will be J dot minus grad phi minus 1 by C del A del T. So the first term is J dot grad phi. You see that J dot grad phi can be quickly written as divergence of J times phi by basically changing the order of the A dot B is B dot A. So do that. And that basically means you divergence of J again is del rho del T, is del rho del T times phi. So this work done basically becomes like this. So work done is basically del rho del T phi is 1 by C J dot del A del T. Okay. So now we put in this expansion over here. And that's where a slightly complicated equation comes out, and you have to do it carefully, but it's not that complicated. Okay. So I'm written down, let me write down, show you exactly when I put in this, the numbers over here, when I put in the rho, when I put in the phi, the expansion of the phi, and when I put in the expansion of the A one. So in the phi, there are 3 terms. In the A, there are 2 terms. Okay. So there are 5 terms total, and see what happens. So we get this term. So this is what we get. So let me again. This is what we get. So there is 1 first term, second term, third term, fourth term, fifth term, 5 terms. Okay. There are 5 terms. The first 3 comes from phi. The second 2 comes from A. Now, if you look at the del rho del T times phi, the third term of that had this 1 by C cube G triple dot. Okay. That will basically combine with the rho to give you a 1 by 3 cubed D dot times G triple dot. This is G dot coming from the rho. Okay. And similarly, the A had a D double dot. This one will combine with the J to get a D dot D double dot. Okay. Sorry, this is not triple dot, this is double dot. I made a mistake about it. This is a triple dot, sorry, hold on. These are both D triple dots over here. Because there was a derivatives come thrice. The J, if you take two derivatives, then you get a triple dot in D. G itself is a dot in D. So now you see something nice has happened over here, if you are careful. There is a 1 by C cubed D dot D triple dot on the top coming from phi. And there's a 1 by C cubed D dot D triple dot coming from A. So I can combine these two to get something which is minus 2 by C cubed D dot D triple dot. This should be reminiscent of your Larmor formula. Your Larmor formula, remember, had a 2 by C cubed in it, right? So we have got a 2 by C cubed terms, but Larmor formula, of course, was D double dot squared. Instead, we have a D dot D triple dot. That's what we have. Combining these two green colored terms. The rest of the terms turns out to be 0. Why? Because, as I said, there is this current conservation which connects the J with the R times rho. So if you use this thing, you will see that the term will go to 0. So what we are then left with? From this very complicated equations, we are basically left with this equation. 2/3, 2 by 2/3 by 1 by C cubed D dot D triple dot. That's where left it. So this whole work done comes to this one small number. And we can rewrite this number. We can rewrite this number like this. So 2/3, 2 by 3 C cubed D double dot squared plus D dt of another quantity. This thing is basically this thing, the summation of these two things. Now, this is what is the work done. Now, if you go back to the initial formula for work done, remember the work done was the rate of change of the energy, which was a total derivative of a quantity plus P. So in the work done, if we neglect whatever is the total derivative, what is left is the energy that is flowing out, the P. So what we do is we neglect this thing. So this is neglected because of the total derivative. So what we have is basically my energy that is going out. So this tells us that this basically explicitly shows that it's not only there's a field outside at some position is such that I can calculate the Poynting vector and find out that that is the energy flowing out, but that Poynting vector, that energy is actually coming out of the work that is being done locally by the charges. Okay. In EM problem, this is something that you have to keep in mind. You have to keep in mind what work is being done locally by the charges and how it's being sort of divided into energy which is stored at some region and energy which is flowing out. And we do this all the time simply, but now we have done it in a great generality. So that's one thing that I wanted to show you because it connects the Poynting vector, it connects the energy flow with the local charge. Okay. Now, you could make it more complicated by basically, or I wouldn't say complicated, you can, if you want to go one step further, then you can basically say how the local work, which was basically due to the local movement of the charges, how that was, can be due to, they have some intrinsic energy or some energy is being supplied to them. So that will be another part. And I mentioned that there is this very interesting point of fallacy which I didn't do. I guess someone has taken it, maybe, where you have a point charge and you see that if you have a traveling wave, that gives you momentum. Okay, so you see how this momentum is transferred to that. So that is something that if I have time, or maybe I'll just put it up, that tells you how the first part can be basically be shown, that the momentum from the wave goes into the momentum of the electron, or whatever momentum of one of the charges. We take the single charge, except that it comes with the fallacy that the charge was at rest, then the momentum charge will oscillate. So the momentum of the charge is at this direction, where the wave is coming like this. When the wave comes like this, only then the E vector is like this. That's why the momentum of the charge is this direction. And the momentum of the wave is in this direction. Okay, so it's a fallacy. One can find out what is beautifully do it, and you'll find that the electron actually doesn't really just go like this. It has some motion on this direction also, which we neglect. It and makes beautiful figure of 8. So Landau, for example, was the first person who calculated this figure of 8, and it's a very interesting problem in EM theory that one can look at. The frequencies of this oscillation and this oscillation is different. One has the double harmonics, the amplitudes are different, but they all oscillate around the common point where the electron was at rest before the charge came, before the wave came. Okay. And also the wave moves the electron a bit, so it drifts. That can also be seen. The sound of the momentum drifts the electron, which we neglect generally. So this is this. The next, I want to look at another extension of our understanding and go a little bit more than the dipole approximation that we did. Okay. So for this, I'm going to start writing, maybe hopefully finish in the next half hour. Okay. So talk about this dipole approximation. If you just give me like 1 minute, I will do something which would be important later. So give me a minute. I want to get rid of all these lines that I drew. Hopefully it will have all the memory. Get rid of the lines. Again, I apologize for rushing through these things. I should have written down, but that will just take already, even this takes half an hour, so that would have taken much longer. Okay, good. I've got rid of all the lines. So that now go to the So let's do a little bit of beyond the dipole. This again will be an expansion. So previously also remember we expanded our linear Virchow potentials in power. So again here I will expand it, but in a slightly different expansion. Okay. So remember again, when we did dipole formula, we had something which was far away, and we expanded the distance. We basically neglected neglected everything which was within this region and only looked at one length scale. That's what we did. But later, we also realized that we can actually, if you want to look at the movement of the charges locally, we can do a slightly better assumption, which is just not have one length scale, but have two length scales in it, in some sense. So what we could do, that we could have this number, we have this quantity that we have, we can write as basically, okay, where this n cap is basically r by r. This is something that we did. So this is an expansion that we did, and remember when we use this, the radiation basically was decoupled into two parts. One part was due to the system as a whole, and then the second part was due to the movement of the individual objects. So we did that kind of, we explained that thing. Now, if we carefully look at this expansion, this thing where we, for the dipole, we basically neglected the second part. We just had the R part of the dipole. So we go back to the dipole and see what the kind of assumptions that we took. We didn't have the n dot R prime part. We just had the first part. If we take the second part, then we have a contribution due to a next level contribution due to n dot R prime by C. Okay. So we will have the phi's. So this was only dipole. Now, again, we have this phi's, okay, which is basically given by R and T, and that is approximately equal to 1 by R integral over D cubed R prime, and then rho R prime, and then a T prime, which was T minus, with this approximation, it will be T minus R by C plus n cap dot R by C. Okay. So the dipole approximation, we only took T minus R by C. We did not take into account the second part. So that's the thing that we want to take now. Okay. That's the thing that we want to take. Also, so for the vector potential also, you know, a similar thing, which will be now approximated as d cubed R prime, then 1 by C J R prime. Aritra, just if I come very close to 4 o'clock, just let me know, okay? Because we don't want to miss that.
Yeah, sure.
T prime over here, okay, which is this T minus, in this case, is 1 by C R prime dot n prime n cap. This part, in some sense, is the time the radiation takes to progress across the source. This is like, you know, the time radiation takes to propagate across the source. So remember, R prime is source. So now if I look at my gradient of this, okay, so if I look at the gradient of one versus this kind of maths is given in your Orfken actually. So if you look at Orfken, Orfken does this in generality. Okay. So a function, okay. So T minus R by C plus n cap dot R prime, okay, by C. Okay. So this we'll see will be basically equal to n cap dot R square F T, and I'm talking R in the sense like now the R is the mean R for this objects, okay? And then I have another term which will be n cap by C plus 1 by C 1 by R n cap cross cap cross. Okay. This multiplied by again del T of by R. Yes. So you can find this out in Orfken. Orfken has, I'm not exactly written in this term, but Orfken has um, uh, examples where what happens if you take the grade of 1 by R, if R and 1 by R. So this I can again write down approximately as minus n cap by C, then del R by R, F, T. some zeroth order of 1 by r square. So this basically gives my 1 by r dependence, because the radiation goes as 1 by r. So this gives me 1 by r. So now I can use this to calculate my B and E, okay, that we can do. Remember, my B field, the magnetic field at R and T, this is basically 1 by C encapsulated. Just look at the formula for by 1 by R, then cubed of R prime, 1 by C J R prime, okay. And my E is basically N cross B. So I can write down my E. This is roughly equal to, again, n cap by C, 1 by R, then there is an integral of d cube of R prime, then del T of R prime D prime minus 1 by C, 1 by R. We will find this formula. We have done this formulas before. We will find it before. 1 by C del T of J R prime. So this last term over here, which has two terms for this E, this I can basically combine into one term, because it has a del T of rho and it has a J, okay? And so what we can do is basically we can use local charge conservation. We can use local charge conservation. I can combine these two terms, okay? Because remember, what we have basically your del rho del T is equal to minus grav of J plus del cross by C del T of J. So this is how we can do it. Anyway, so whole point is that you use this, and your E, as usual, will be basically minus n cross BR. Now we have got E and B, so we can, now we are bringing the far point, the field point approach again. So we have gone back to the field point approach. We're not doing something the work done approach of half an hour back. Okay. So now we can calculate my S. So final results is interesting. So bear with me a little bit. So my S, my flux, okay, is basically C by 4 pi E cross B, which is equal to C by 4 pi E squared. Okay. So I can write down my N cross S. Okay. This is what is going along this direction. So I can write down as 1 by 4 pi R squared. Okay. Then 1 by C cubed. So C's are coming from before. Basically plug these numbers in. Okay. Then this will be n cap cross d cubed R prime del T of J R prime T. Then because it's a B squared, so B squared, squared. Okay. So then from this I can write down what is the power per solid angle. Into the power per solid angle, this R squared goes away. This R squared in the denominator goes away. So then this basically gives me my power per solid angle. Okay. And so this is basically R squared into n cap. So this R squared just goes away. That's it. Now, as we said, when we did this thing previously, we did not take into account the 1 by c in cap dot r prime term. Okay, so previously we neglected the n cap dot r prime term in, this is what we neglected. And so then previously, therefore, so we got, when we calculated this, we got my dp d omega, which is the power per solid angle. This we basically got as 1 by 4 by c cubed, and then there was an n cross summation of 2i ri double dot I equal to 1 to whatever this whole square. So this was the dipole thing. Okay. So we got the dipole formula where we had the QIRI is basically D, and so the D double dot squared. So it went as the square of the dipole. That's what we got. Now, of course, we want to include this term. Okay, so we want to include this n cap dot r prime by c, this correction, this extra part, the second order part we want to include. Okay, and so when you include this, let me call my t prime. So when I include this thing, okay, so let me sort of define, okay, t prime as I don't know, t system or whatever, t local L, t doesn't matter, t local, t of the tq, because these are the charges. Okay, so which is basically, which is same for all the charges. Just define it like this. So then I can write down n cap dot r prime del t of j. Okay. This, because I have only one t over here, okay, because it does not differ between the locally, I've neglected the differences between the local small t differences. They are same one. This del t becomes a d dt basically. D dt of n cap dot r prime j prime. Okay, this is what happens. So now this becomes something very interesting. So you have an n cap r prime j prime. So what we have got now, okay, so we need to calculate now what. So we need to calculate this quantity d cube r prime j at r prime and tq plus 1 by c. Right. This is what you want to calculate, because now this is what is the thing that you want to calculate. Okay. This is basically the same for the whole region. So once we put this, so do a little bit of calculation. Once we put this back over here, just do the expansion, calculate for both, you will see this is equal to something that we know before, which will come due to the TQ that we have already done. Okay, this is my d dot, which is a plus, due to the second part over here, another term will come, right? So the second term will be d cubed r prime 1 by c actually there is this 1 by c over here also. Actually, d cube r prime 1 by c n cap dot r prime then del t of j. So this is basically, if I look at like this, I can take out my del t outside because I'm neglecting the small differences between each of them. Plus 1 by c d dt of d cube r in cap dot r prime g. Okay. This is what it is. So over here, I'm going to play around with this second term. Okay, this term I'm going to play around with this term. What I'm going to do is I'm going to write this term as two terms. Okay. So what I'm going to do is I'm going to write this like this. Write it, this whole thing as 1 by c d dt of integral over d cube r prime. Okay. Take the n cap out, n cap dot half. So remember it was rj, r prime j is two vectors. I'm going to write it as a sum and difference. So I'm going to write it as half of r prime j plus j r prime plus half of r prime j minus j r prime. Okay, so this is what I can. So I've done this trick. Now, when I do this trick, if you look at these two parts, there's the first half into whatever and then the second half into whatever. This first thing, this thing, okay. If you look at carefully, this is basically the next multiple. Okay. So this is the quadruple. This is the electrical quadruple. And you know that electrical quadruple in general, remember when we were looking this wire in which the electrons were moving, we saw that the powers was v squared or dipole, v by c squared for dipole, then v by c to the power 4, so it's subdominant than the dipole. And in this case, actually, basically 0, and so we can neglect this. So we can neglect. So we are only left with the second part. Therefore, this thing that we had over here, this thing becomes equal to, first we have a d dot of dq plus I have a second part which is, sorry, this plus will this become minus due to minus. So the vector algebra will give you a minus sign actually. d dt of d cubed r prime n cross 1 by 2c r cap cross j cap. This is what it is. J cap is of course at r cap and t cap. This is something we're getting. Now, if you look at this, what is this? This is something very interesting, right? What we have got over here is this 1 by 2c r cap cross j cap, an integral with d cubed r, that is nothing. So if I take this thing, this d cubed r integral 1 by 2c r cap, that is nothing. Till now we are looking at the electric dipole moment, but what we have landed up in the second order is basically the magnetic dipole moment. Okay. So when we do this correction, we have an effect due to the magnetic dipole moment of the charge configuration also. So what we now get basically is d dot of dq minus n cross mu dot. Now this mu is basically 1 by 2c integral of dq r cross j, which is the magnetic dipole. Okay. So we have got over here terms contributing from the electric dipole moment plus term contributing from the magnetic dipole moment. Okay. So now we are now ready to calculate what is the power. The power, remember, was c by 4 pi c e cross e or b squared. So I have to take the square of that. So now I can calculate the power. Therefore, my dp this will be 1 by 4 pi c cubed, okay, n cross then d dot d double dot, sorry. There's a d double dot over here. Okay, I think I've always wrote it as d dot. It's all d double dots. Right. There is a d double dot over here. The d double dot over here. D double dot over here. All d double dots. I all wrote d dots over here. Remember, these are all d double dots. I'll correct it when I write it. D double dot minus I think I'm making some mistake over here. Oh yeah, n cap dot. When I do something hurriedly, it comes. This whole square is coming because your S had E cross B, so it was B whole square, so that's how we get whole square. So then this is basically our familiar 4 pi c cubed n cross d double dot whole squared plus n plus double dot whole squared plus 2n dot d cross mu. This is a interference term. And remember, d and mu both are linearly related to n cap. So this term goes to 0. So what we have finally is your dp d omega. This comes out to be due to these two terms. Okay. Now if I integrate it over the solid angle to get the total power, so now you will have an equivalent quantity coming from your magnetic moment. So your total power radiated power, it is an integral of dp d omega. This will give you, so first of all, this thing will give you your dipole pattern, but then you integrate of the dipole pattern. So you'll get exactly by 2 by 3c cubed. But instead of d double dot squared, which is what we got, remember the last time that is what we wanted to do, we'll also have a mu double dot squared. So this is now my new Larmor formula. So if we do it correctly, so we not only have in this approximation of charges which are locally that we can think of the whole charge configuration as a dipole, we not only have a dipole because we have currents in it, we also have a magnetic dipole rather than an electric dipole. So now you can calculate what is your E and B, and if you calculate your E and B, you will see an interesting thing that at the Faraday field, just like the magnetic dipole, just like E and B has a symmetry of total results, that result will be symmetrical when you transform from E to minus B, E to B and B to minus C. At the same time, if you change D to minus mu and mu to D, you will get the same results. So there is a symmetry in the results also. So this is another thing I wanted to show you, tell you that magnetic dipole is also there. Electric dipole is not everything. Most of the places they will just tell you that the simplest formula when you use Nama's formula, you have the dipole formula, but there is a correction. This correction, of course, is subdominant, is a 1 by C subdominant, but there is a correction. And that correction comes with the magnetic dipole. There may be regions, for example, neutron star, magnetars. Over here, you could not have done it correctly if you have neglected your magnetic dipole. Right? You want to calculate the flux of something, your radiation that is coming out of a pulsar, neutron star. You must also take into account your magnetic dipole, not only electric dipole. So over there it becomes important. So that's what I want to stop today. I think exactly on time, 5 minutes left, but happy about it. I would not have done this unless I have written it down the first part. Next day, we are going to try to go as quick as possible to actual processes. So we will probably do synchrotrons and Cherenkov and X-rays and stuff like that, and try to wrap everything in the next 3 classes. Okay. Remember, we have a class on Sunday. So if we have a class on Sunday, then 2 more classes in next week. Hopefully, I will try very hard to wrap up. But that would basically mean there are a lot of things I won't be able to say, but I think we have done quite a bit. And if you have already, learned sufficiently from this course, then you have learned quite a bit. So that's it then.